This is a presentation recently given at the ICCAS 2015 conference covering the generation of whole surface from laser point clouds. Over the last few years, a lot of the developments in PolyCAD have focused on capturing surfaces from existing geometry. For example, that might be information held in images that have been created by scanning plans, sections, or other surfaces that may have been part of solid modeling definitions that have now broken. And this use of laser scanning is kind of an extension of that strategy to kind of rebuild surfaces from existing geometry information. The only challenge with laser scanning is that we're now dealing with a considerable amount of data that can be in the gigabytes, and it's not always clear the quality of the data. So the key points of the presentation is that compared to other areas where optical scanning is used, this is a slightly different challenge. When you scan a ship or a boat, it's outside of its normal environment. It's not floating, it's in a dry dock. When it's in a dry dock, it has to be supported by structure that would obscure parts of the surface. And often there's work going around the outside that may stop you getting a good view of the ship. And there can be work that may influence the laser scan head. Following the scan, when we need to go through the process of turning that geometry into a surface, what's happening at the moment is there's a lot of generic solutions out there that you're using simple fitting algorithms for surfaces, and they find it a challenge to account for this particular scenario. And this means that some of the surfaces that are being generated are often too complicated for the engineering analysis that we need to do. They can be relying on solid modeling, or they can have a lot of points. The marine industry has been defining surfaces suitable for its engineering analysis for decades now, and I feel that it would be a much better approach if these solutions were enhanced to accommodate laser scan data inside the applications. This is obviously what we're going to do, and if we're going to do something, we like to do it right, so why not utilize all the information and the technology to try and find and deliver the best approach which gives you the best definition in the shortest amount of time. So let's have a look at the current situation. So here is a scenario which shows a laser scan head in a non-marine environment. It's scanning some plant. We can see that we have some concrete columns and a lot of pipes. So the challenge with the optical scanning process is that it can only capture what it sees. It can't capture the other side of the concrete columns, and it cannot capture the other side of the pipes, because from this position we cannot see them. We can capture it by moving the scan to a new scanning head to a new position where we take another scan, and throughout a sequence of these scans we can build up an almost complete image of the area that we want to survey. We say almost complete because there will always be areas that are a challenge to capture. There will be areas that we cannot see because we're restricted on access, or there may be safety implications from going to those places to scan those locations. So within this area, for example, areas where there's complicated piping, perhaps at the bottom of the upper floor, might be more of a challenge than other areas. But this is part of a much wider process. Once we've collected a number of scans, we will go into the software environment to register them, to make them all synchronized together to get a proper survey set of data. Following that, we would clean the data up. The example would be that if you were scanning inside a dry dock, then you would want to remove all the information that was captured about the dry dock itself, leaving just the ship definition inside it. After that, we have a survey, a set of data that we can use to fit the surface. We would take the data to another piece of software, and we might need to use a person with other expertise to generate the surface there. Following that, we would then want to use the surface. Again, this most likely will require another person with different expertise, and it will be likely that we need to take that surface through a set of interfaces to make it compatible with the other system. that person that's using it might not be in the same organization, they might be using different pieces of software, so there's the chance that different systems and time between sending things might make the data degrade over time because of the different software that's being used, or people might modify the data. So let's have a look at this process in a little deeper. This is an image of a museum vessel, a submarine, that is in a dry dock. This is actually quite a good, well exposed surveying environment. We can see the exposed hull surface towards the upper area of the image, but then along the keel we have all the keel blocks that are supporting the vessel, and if we were to scan this, then this area would be quite complicated. Certainly it would be very, very challenging for an algorithm to automatically determine the surface shape in this area. So we would need to turn to the human to distinguish between what is useful for the hull definition and what needs to be excluded as part of the dry dock structure. This isn't a vessel that's currently in operation. A commercial ship, for example, should spend as little time as possible in dry dock because it's not earning money while it's there. While it's there, it will be worked on. There'll be staging and scaffolding around the outside. There may be machinery that influences the scan head by imparting vibrations, say for example a cherry picker with a single cylinder engine. So all this can affect the scanning process, and we might not get the perfect solution that we were looking for. And as it's expensive to rescan things, sometimes we have to deal with the situation that if the scan hasn't gone well, we just have to accept the data the way it is. Some examples of some scan data. This is the first data set I dealt with, a 48 meter schooner. This data set consists of 250 million points. I believe it was surveyed at night in a floating dry dock, and we can see that the colour definition is quite poor, even though I've enhanced it as much as I can. It's a detailed scan. We can see the anchor chain, we can see all of the deck arrangement. If we zoom in a little deeper, we can see parts of the hull form. We can see rivets and some of the structural banding from the keel. We've got the propeller. In fact, we've got two images of the propeller. It looks as though it was moved during the process. On the deck, we can see the wheel, any mooring. We can actually see the planks of the deck, so some quite good definition there. If we go to a well-lit area like the accommodation, we can see a vacuum cleaner. There's some hard hats, a stool, even cups on the table. But from a hull generation perspective, all of this information is not necessarily what I need. Within reason, I need something that's fairly simple. So really the objective is to find a way to make this data accessible from a naval architecture point of view. A simple way of doing that is to just intersect the cloud with planes, and we see that we got here what looks like curves. They're not curves, these are just the data points associated with the planes, they're close to the planes, but there's so many of them it looks like we're looking at a curve. But this is a nice way of accessing the data and seeing what we've got to deal with, and gives us the opportunity to start to plan how we'll put the surface together. At the other end of the spectrum we have a mega yacht here. This one only has 8 million points, and when we look at the image we see that the top sides of the hull surface are missing. We'll come to that later. But even in the underwater section we can see quite a lot of white areas where the scan hasn't really captured it that well. If we go onto the contours we can see quite a lot of gaps, and we can also see some of the appendages as well, such as the stabilizers and the rudders. And these will be items that we might want to exclude from the surface. We would include them as separate objects because the surface needs to be as simple as possible, perhaps for our engineering analysis software. Perhaps we're interested in some stability work. This is a photograph of the survey environment. We can see here that the top sides of the vessel are very reflective. Because of that, they would not have returned the laser back to the survey head. This can also happen with submarines that have a very absorbent surface where the laser just doesn't get returned at all. Both of these situations highlight some of the practical challenges that you need to deal with. Despite that, this is a very open scenario for scanning the ship. We don't necessarily have a lot of supports around the vessel. It's not in a confined area. So certainly for the below the waterline area, we should have got a very nice complete scan, but we didn't, and that's the way it works. Moving on now to look at surface generation. This here is the example of what was done with the Schooner in some other surface fitting software. We can see that the process mainly involved draping a surface over the data. We end up with a surface that has quite a lot of control points, and this is a particular challenge if we want to do anything with the surface, because we've got so many points that even small influences on an individual point will cause the surface to become unfair. We also can see that as we've draped the surface over the hull, then there have been no areas where we've tried to capture the features of the surface. So there's no control points particularly focused on the boundaries of the surface. We can also see in the shading a clearly defined rabbit line between the keel and the hull surface, and that's not captured in the surface either. So we've got a capture of the surface. It's probably most likely quite smooth, but it's not necessarily got the particular details that we might want to be captured in the definition from a naval architecture perspective. So as we've got such a large surface and we haven't really captured the boundaries, we need to take it a stage further, and that can be done using solid modeling tools. We can trim the surfaces, we can use more surfaces and build a complete definition. Solid modeling comes with challenges. These are complicated mathematical libraries that involve numerical algorithms, they involve tolerances. Different CAD software have different implementations. When you take one definition from one system to another, it may be changed, it may be altered, the tolerances might not be accepted, and over time gaps can appear. This is just the way that it works with solid modeling. The challenge for a lot of the analysis software is that to have a solid model incorporated in your tool is quite expensive or quite complicated to use a free library. So going directly to the solid model can exclude you from doing certain types of engineering analysis. Ultimately, we'd like the definition a little bit simpler. So to summarize the challenge, at the survey end, we're dealing with something that is got a lot of practical implications. We're just optically scanning a surface. That process is subject to noise from the environment or just from the process, which means that we might not get everything that we expect to get. A shiny surface can completely stop the laser from being returned. So that might mean at the end of that process the laser cloud is not complete, and we might get other features such as all of our dry dock supports or appendages that we might not want in our final version of the surface. We might want to do something else with those. So because the cloud is not necessarily guaranteed to be complete, the opportunity to use automated surface fitting is lessened somewhat. You have to make allowances for it. And in the second case, we saw a typical example of a surface being fitted to a hull form, and we had to deal with a case where we have a rather complicated surface with a lot of control points. And because we've overlapped the boundaries, we've then gone on to use solid modeling to try and put that into a nice tidy surface. So neither of these cases are particularly good from an engineering perspective, where we've kind of got to use a lot of, I suppose you could say, workarounds to get the best out of the data that's there. So maybe we can find a better approach. In the marine world, certainly for commercial vessels, commercial ships, the the hull definition process is often different. It's often using a lot of curves rather than directly manipulating the surface. Curve networks are a good tool for controlling the different details in a hull form, particularly for a ship. We have areas such as the flap side, which are planar. These areas don't really need much definition. We can get by with a few number of surfaces or even directly as a plane. But then in other areas of the surface, such as around the bow, around the bulb, where we've got some quite sharp curvature, we need to get the right definition in those locations to allow for the correct steel production process and the sharp corners that are there. So the curved network allows us to make an irregular pattern of shapes. We can have coarse areas where it's flat and quite detailed areas where there's a lot of curvature, and we can transition the shapes from one to another by just depending on where we put the curves. The relationship between the laser cloud in terms of the curves and the actual curve definition is clearly highlighted here. Back with the Schooner, we did some simple cuts of the cloud using some planes, and we captured some what looked like curves. These were just sequences of points, and we can fit curves to sequences of points very easily. So what we have here is a very easy process that we can use to selectively slice through the cloud in areas that we feel are good and generate a curve for this type of surface definition very easily. Highlighting that in more detail, what this process does is be very selective about where it captures the geometry from. This view is showing a fairly tidy view of the survey, but we see that we have those appendages there that we might not want to put into the surface. And by using planar cuts to generate a curve, we can selectively look at where we're going to put our definition around the surface. We can choose the best locations, we can choose locations that are going to avoid any problem areas within the point cloud. So focusing now in more detail on the curves, we've got the capability to do a lot more with the curve definitions than we have with the surface. This is just a sequence of 8 control points, and depending on how we want to interpret the control points, we can get different types of geometry. We can start to define what we want from these control points. In this second case, we have a cubic spline, a case where the curve interpolates the points rather than just approximates them, as in the case of the B-spline. We can apply some specific features. We can apply our design intent to the definition. We can get a straight segment. We can get a knuckle. Internally, this has the effect of splitting the curve up into multiple mathematical definitions, but as far as the user is concerned, this doesn't really matter at all. So it's quite a good way of getting different shapes into the curve to put in certain features that we'll find in the whole surface. And we can apply these ideas to that curve network that we saw earlier. We can apply constraints to individual curves so that all the other curves that intersect with it behave in the same way. This is a scenario that shows a sequence of sections fitted through 4 curves that control the longitudinal shape of the vessel. If we change the constraints on those interior curves to tangents which are parallel to the curves that they're connected to, with that small change we quickly see that we can get a shape that represents a ship very easily. Of course, we have some other constraints that can create some slightly more weirder shapes. For this particular scenario they might be inappropriate, but there may be others where these types of constraints may be useful. So we have a set of constraints and we can use them within our curve network, and they'll be found under the main curves that separate different areas of the whole shape from each other. So the constraints on these curves will be used to make sure that the curves are compatible across those boundaries, and to reduce the amount of work that we need to do to make sure that these curves have the correct tangency in those locations. So by applying a description, these curves automatically pick up the correct shape without us having to do any precise mathematical configuration of points. So we have a way of controlling or setting up a structure in which we can get the hull form. Now we need to go through the process of finding a way to get the shape of our point cloud into the curves that we're going to pick from it. This image is a cut through of the Schooner survey data. Now if we look a little bit detail, we see the kind of things, the quality of the data that we're dealing with. It's not perfect. It clearly shows where data has been obscured because the laser cannot see it, and it shows the level of noise that we're dealing with. So as the data is not perfect, we need to find strategies that help the way that we can manipulate and access this data. One of the ways is by putting the data inside a map. This makes it far easier to find ways of accessing the points, because by looking in the cell we can find all of the points located around the area rather than having to search every one. And we also have the challenge of dealing with a considerable amount of data. For example, if we slice a waterline through a hull form such as these, we'll find that we get around 100,000 points. Putting 100,000 points in a fitting algorithm is possible, but it's a very slow process. Certainly a curve won't be fitted in an interactive amount of time. So alternatively, what we could do is take a single point from each map cell to reduce the number of points that we're fitting to. Without reducing the accuracy of the curve, we still have around 1,000 points, and this makes the process of fitting a curve to this data much quicker. An example would be such as this, where we have our network of map cells and we obtain a single point from each cell. The map cells also help us to understand the structure of the data. We can establish the adjacency of points and connect them into a nice tidy curve. That doesn't always work. In areas where the cloud is poor, where it's got holes, we can get a different result if we're not particularly careful in the way that we connect things together. A simple sort of adjacency doesn't always work out well. We have to find another strategy. One way of doing that is by using the network of map cells to create the idea of shortest routes through the survey data. So here is our points obtained from each cell, and if we try to find the shortest route from one direction to another, and we give ourselves the opportunity to jump sections of the curve, we could end up with curves like this. So these two cases where we have a support on the side of the hull form, this kind of solution allows us to ignore that support data, because either it's disconnected, or by following that boundary it's a far longer way to go than it is if we just jumped through the most logical route through the data. So now we've got a section of points and we know how they connect together. Now we can fit a curve to that data. The most logical algorithm to use in this particular case is least squares. These are very good for fitting B-splines, as well as the kinds of mathematics that we might have dealt with at a school level understanding of this kind of problem. Least squares has advantages over other algorithms such as cubic spline in that it gives us the ability to stipulate how many control points we want to use to fit the curve data within reason. Now we must remember that this curve segment is probably connected at the ends to the curve network, and at the curve network we have our attributes, the shapes that we want that part of the hull form to be, which means that there are tangents applied to this curve. And we can incorporate that into the algorithm by reconfiguring the solution process, adding a few more equations. We can calculate the curvature qualities of the curve. It might not be good. If we wanted to improve that, we could further extend the algorithm to add some smoothing, and we can improve the characteristics like that. However, when we do introduce smoothing, it means that we're starting to make the curve diverge from its original fitted data, and that might not necessarily be the thing that we want to do, but it does mean that we have the opportunity to make it smooth. So we've got a decision there. That's something that the user interface can allow us to address. It gives us some parameters to work with. We can see how the curve responds to these kind of parameters. We can determine the number of control points that we're going to use on the curve, so that we can make sure that we have consistent mathematics across the area of the hull. And this gives us an opportunity, this kind of display, to pause, because we have to review what we're doing, and that gives the user the opportunity to think ahead and to plan their best approach. So it stops them kind of rushing ahead and just makes them think about the quality a little. Let's apply both these solutions to this particular case of fitting a curve to an intersection and playing a slice through this data here. So if we take the points from that slice, we get something that looks like this, a sequence of points. And if we fitted a curve to it just simply, then using the least squares we'd get a set of control points that were pretty much uniformly spaced. On its own, this kind of approach doesn't pick up the structure of the whole form. It doesn't account for the area of flat side where we've got a straight segment. It wouldn't account for the stem rounding. So in the straight segment we've got far too many control points than we really need, and in the rounding area where it's a lot smaller we don't really have enough control points. It's only 2, it's only really controlling the tangent. So to try and get the best shape here we would have to either increase the number of points so that we have quite a lot, enough on the at least the rounding to take account of the uniform spacing so that everywhere is okay, or do something else. So what we can do is use the curve network, the information within it, to separate the different sections of the fitting process. We can make them correspond, and remember again that we have those constraints on the curve network, and what these will do is apply tangents in each direction to make sure that this curve is configured correctly to fit up the shape of the whole form that we're expecting. And then when we go and fit curves to this, rather than fit one single segment, we're fitting 3 segments. The straight segment has no points on it. The shape segment has uniformly spaced points with the correct tangents at each end. With the stem rounding we have a decision. We can use an automatic algorithm to create a simple arc shape, or we could fit that in more detail by using exactly the same process that we have in the shaped area. The interface for this gets a little bit more complicated. Rather than one segment we have to account for the different segments, and we give the user the opportunity to independently control the parameters and the fit for each of the segments independently. So we'll now put that whole process together for a complete survey dataset. Going back to the Schooner, we can go and have a look at the underwater section, and again we'll highlight those missing sections of the surface which we can see more clearly when we look at the kind of the intersections around the contours of the vessel. And the first stage is to create the core curve network, the one that contains all the characteristics, the constraints. For this particular vessel it's not a particularly helpful network. It's the shape of the ship doesn't have a clearly defined parallel middle body. It just has some outer shapes. Along the keel we have a blend, and because most of the curves in this area are focused around the keel, which is quite complicated, it's got a lot of supports, it was quite a challenge to find the correct shape in that area. It took quite a lot of time to humanly interpret what the cloud was trying to tell us. But once we define these curves, then we can quickly go ahead and create the shape curves. This happened very quickly. We just make our plane, define the plane, slice it, and then fit a curve, and all the curves have pretty much the same number of points, so they're all consistently generating the same kind of mathematics. Following that, we would slice or connect up the curve network in the other direction using some simple B-spline curves that are fitted using a cubic spline. And now we have a complete surface. We've got space for a lot of patches to be generated. Reduce a surface like this, we can see the contours here. We could compare these curves visually with the contours that we've cut from the optical survey dataset. Of course, we could go on and analyze the curvature. It's in general not so bad, but there are areas where the patches start to elongate, that the curvature gets a little bit less than desirable. So that would be the complete process, and we move on to talk a little bit about the performance of this process. For the shape curves themselves, that process can be generated and done in quite a quick amount of time, 20 minutes, which is far quicker than you would be able to do through normal manual means. However, we did need the core curve network to start with, and that can take much longer, particularly in this case because most of the curves were located around the keel, and because the keel has got a lot of the support areas around there, it was very difficult to understand exactly what was going on with the shape. A number of case studies have been done using this technique. The case before last looked at creating the hull definition for a Type 23 frigate. This was an interesting case study because it was not done by me. It was done in a commercial environment by people who had to learn the software. And this was the first time that we encountered the need to validate the surface properly. And the validation was needed not only so that you knew whether the surface was accurate, but you had the information to communicate the level of accuracy to your management and to your customer, who might not have been so well versed in what you were trying to do. Subsequently, the project involving the 48-meter mega yacht was the first to actually use the validation process during the generation of the hull form, so this means that this was a process where we had the validation process to drive the accuracy of the surface. So, returning to that and the validation discussion itself, this would be the desirable kind of definition that we would want. A case where the surface is right outside the survey cloud is very easy to pick up. We can see it graphically because when you render the surface, all the points are on one side of the surface, not on the other. The challenge is to deal with the other cases where the surface is very close to being accurate, but how accurate is the question. This is a typical situation that we might have to deal with, where the surface is kind of oscillating from one side of the cloud to another. Actually, this is quite an easy case that occurs because when we fit our shape curves, indicated by these two dots that would be going in and out of the screen, then when we come subsequently to fit the B-splines by the cubic spline, because we're just splining them, the mathematics of the hull shape itself might not be compatible with the curves that we're fitting. So we can get some small oscillations. The question is this too much? Are we there? What's the level of accuracy that we're actually getting there? Is it acceptable? So we've got to go and measure this. And we have to consider that we have a considerable amount of data, and if we're not careful, it's going to take some minutes to do the analysis. So rather than doing a full three-dimensional analysis, we can start to simplify things simply by just analysing normal to the surface. Then we only have to measure in one direction. We'll of course take the mean, and we have to remember that in this case, neither of the mean from the point cloud or the surface is the concept, has the concept of truth. The point cloud is surveyed, it is influenced by the statistics of the measuring process and the environment, and in the same way the surface is just a product of that data in the first place. So really we're just looking at how closely these correspond together. So the mean is one measurement. It tells us how close absolutely we are to the survey data, but of course if the survey data is noisy or very accurate, we need to give an indication of how well the survey data supports the level of accuracy we're looking for. We could look at quantities such as the standard deviation. Although this is a very common measurement in statistics and engineering, as engineering dealing with the kind of measurements that we're dealing with, it's not a quantity that we have a lot of feel for. Based on a cloud, just appreciating the standard deviation of the thickness is quite difficult to do, so we probably need to come up with a far more practical quantity. So I chose the thickness of the cloud, and experience so far suggested that this is quite a robust measure because we don't really have individual outlying points. Normally the cloud is quite well behaved, so the thickness is consistent generally across the measurements. And then we need to think about how we display this data, and the ideal way is to go for the most graphical way possible. So this image shows the mega yacht with the green area within the 10mm absolute tolerance we've defined below. Red areas are areas of the surface that are outside of that. Areas that are clear are areas of the surface or survey scan data that don't support the conclusion because there isn't enough data. Once we've calculated these statistics, we can then analyse at different levels of tolerance. If we increase the tolerance down to 5mm, then we can see we've got a lot of more red areas. If we take account of the side that the surface is on, we see that scenario described previously where the surface is oscillating from one side of the cloud to another. And then if we look at that sidedness with respect to the thickness of the cloud, we can see that the cloud is actually much thinner than the oscillations in the surface itself. and we need to appreciate whether this is something that we need to consider as being important or not. As well as the graphics, we can still produce numerical statistics. This would give a global impression of the surface in terms of its mean error and its standard deviation, but this doesn't necessarily on its own give us a good feel for how well we're doing. Obviously with graphics we can go to other renderings. This is an illustration of the surface being shaded with gradients to highlight areas that are worse than the other. So this can be used to target those areas of the surface that are worse than others. And in this image we can see the bilge keels and propeller areas and rudders highlighted as the red areas towards the bottom right of the image. So bringing this presentation to a conclusion, to summarize what we've talked about, as we've presented here, the present approach is really a series of disconnected solutions that have come from other areas of engineering. We have the surveying, that when you go to dry docks it can be a difficult environment to scan, certainly for ships. There's areas that you cannot see. There's practical effects that can make the survey difficult to proceed with, such as the reflections. And then when you actually look at the process of turning that data into a surface, for hull forms, because there's some challenges within the area that's being surveyed, then you need to have something that you can use to influence the surface to be able to selectively capture which parts of the laser scan that you're going to use to generate the surface. And because some of the surfaces being generated are a lot more complicated than what we really want to be using inside the engineering domain, and we have a lot of surface generation tools already in the marine domain, well, it'd be nice if we could take that laser scan survey data into the surface definition environment. And the key takeaway from this research really is that you don't really get to see the quality of what you're producing until you introduce validation into the process. It really makes for a productive experience. It allows you to communicate the level of accuracy to your manager or to your customer, and it allows you to be directed to those areas of the surface that are in most need of correction. So thank you for watching. Here are some of the areas where you can get more information, either by looking at the web page or contacting me directly by email.